Okay. So what did we cover in the last session? Let's summarize what we covered in the last session. We started with recursion, right? And we said recursion has a lot of applications. One of the biggest applications is life itself. In computer science, almost all algorithm design techniques make use of recursion. Decrease and conquer, divide and conquer, dynamic programming, backtracking, branch and bound, etc. They all make use of recursion. So we need to understand recursion. So not just that, and why we introduced recursion so early, right? We haven't started looking at algorithm topics, but we still introduced recursion pretty soon. The reason is next we are going to look at trees, and trees is an inherently recursive data structure, right? Of course, you can implement all the algorithms on trees using non-recursive algorithms also, right? In a non-recursive fashion. As we said, any algorithm can be written both recursively and non-recursively. And we saw some of the pros and cons of these. And we looked at a couple of problems. We looked at decrease and conquer approach, right? What is decrease and conquer? A subproblem gets, okay, so let's define something like this. So you have a subproblem and that gets reduced into another subproblem, and this subproblem, if this original subproblem is of size n, this can be of size, say, n minus some constant, or n divided by constant, so on, right? But there will be only one subproblem. There is only one subproblem. And again, this keeps getting divided until the subproblem size is just one, right? One or even constant, then you will solve it. So this is decrease and conquer, decrease and conquer. So what is divide and conquer? We also saw divide and conquer. So divide and conquer means you split the subproblem into two or more subproblems. That means you recursively execute them also. Binary search, you divide it into two groups, but you only recurse on one of it, right? So whichever executes, that is important. How many subproblems will get executed? Only one. So we call it as decrease and conquer. So divide and conquer, we saw in the case of array sum, you split the subproblem into two or more subproblems of size maybe n by some constant, right? N by constant. And so on. I mean, there can be more, but there should be at least two, right? Okay, so this is decrease and conquer. And then we also saw non-recursive way of solving some of these problems. So whenever we use a recursive approach, right, like this decrease and conquer or divide and conquer, we need to have space for the implicit stack used, right? And we also said that we can convert these solutions into non-recursive solutions. See, a recursive decrease and conquer can be written as a non-recursive decrease and conquer solution. Similarly, a divide and conquer, a recursive algorithm can be written as a non-recursive divide and conquer algorithm, right? But some of it is more complicated, so and it is out of the scope of this course, okay? But for usual ones, I mean, you have seen how we converted recursive binary search into non-recursive binary search, right? So on. Anyway, so that's one thing. And second is typically decrease and conquer is slower, right? It is slow. In practice, you want to write a non-recursive version, but it is easier to analyze all these decrease and conquer algorithms because you can write a recurrence. you can easily construct solutions based on this recursive relationship, right? Okay, so that's about it. And what else? Did we discuss anything else? Typically, divide and conquer can lead to, might lead to, not always, right? But typically might lead to faster algorithms than decrease and conquer. So typically they can reduce the complexity. Whatever we saw, right? Maybe product A times B, and we saw that using divide and conquer. No, was it using divide and conquer? No, it was based on decrease and conquer. Probably we haven't seen a divide and conquer that is reducing complexity, right? But later in the divide and conquer topic, we will see a lot of algorithms that improve the time complexity asymptotically. Okay, probably we haven't covered asymptotic improvement of divide and conquer algorithms here, but at least you need to know all these terms, how to analyze these terms: time complexity, space complexity, and implicit stack space. What else? How to convert simple algorithms from recursive to non-recursive, non-recursive to recursive, and so. Okay. Yeah, let's continue. Fibonacci number, right? So you might have heard about this Fibonacci number, and Fibonacci number is defined as n minus 1th Fibonacci number plus n minus 2nd Fibonacci number. Okay, so as n depends on the longest history is n minus 2, you need to have two base cases, and we have two base cases. If n is equal to 0, it is 0. If n is equal to 1, it is 1. Okay, and we get this table. This is the Fibonacci numbers. Simple, right? Simple recurrence. And you can generalize it also. Instead of every number is the sum of last two terms in the series, you can also write sum of last three terms, sum of last five terms, right? Those are kind of generalizations of Fibonacci numbers. I think they are called Lucas numbers or something like that, right? Anyway, okay, let's come back. So here is a simple recursive algorithm. Is this a decrease and conquer? No, it is not a decrease and conquer, right? Because you're calling both these subproblems. Is this a divide and conquer? No, this is not a divide and conquer. Why? Because the subproblem is reduced by a size just 1, not by a factor of 2 or by a factor of 3 or something like that. So this is not a decrease and conquer. This is not a divide and conquer. This is some recursive algorithm, some recursive, right? Okay. So how do you write the time complexity of this? T of n, let T of n be the running time of this algorithm, right? Then running time of this algorithm f of n is running time of this subproblem and running time of this subproblem, right? Plus some constant number of operations here, if n is greater than 1. If n is equal to 0 or 1, it's the base case constant number of operations. And there is a proof to show that this is of the order of theta of phi power n. And what is phi? Phi is the golden ratio. Do you know about golden ratio? 1 plus root phi by 2. So I think it is approximately 1.6, something like that. It is an irrational number. And they say that, so this golden ratio, so any object that has this golden ratio is beautiful. For example, in Italy, there is a structure, right, whose length is to this breadth is golden ratio, right? Approximately equal to golden ratio. They say this is the most beautiful rectangle, right? Where the length is to breadth is equal to golden ratio. And I think Leonardo da Vinci, right? He has created a diagram of a human. I don't know, it might be something like this. in a circle, right? There is a name for this. Check that painting. And he gives a lot of golden ratios, right? With the hands, face size, and so on, right? Legs, body length, and so on. So he shows a lot of golden ratio. And there is a claim that a person who has a lot of these ratios in this golden ratio format, they look kind of beautiful, right? So there is a way to, people have tried to objectively measure beauty, right? Golden ratio is one of the terms they use. Okay, so check this. This is a very interesting account. Anyway, okay. So this is a simple recursive algorithm. Okay, let's try to write the execution of this recursive algorithm in a tree format. Recursion tree. We call this as a recursion tree. Okay, suppose you call f of 7, Fibonacci of 7. Fibonacci of 7 calls Fibonacci of 6 and Fibonacci of 5. F6 calls F5, F4. F5 calls F4, F3. F4 calls F3, F2. So on, right? Until the leaves of this tree, look at the leaves. Leaves of this tree, all these are the leaves, right? Are the base cases. What are the base cases? N is equal to 0, N is equal to 1. These are the base cases. F0, F1 are the base cases. Those are the leaves. That means no more branching for the leaves. The branching ends at the leaves. Okay, if it is not a base case, then it is a recursion case. There is branching. Fine. What else can we infer from this? Suppose we consider F5, right? F5, computing F5 is a big subproblem. But once we have computed, we still compute it again and again and again, right? See, we computed F5 here. We are computing F5 again from scratch. So this is exactly the tree we have here. So this is recomputations, right? So in Fibonacci, normal recursive algorithm, there are a lot of recomputations. Now think about f of 4, f of 4, f of 4. How many times f of 4 trees exist here? 3. Okay, what about f of 3? Let's see f of 3. 1, 2, 3, 4, 5. Do you see the pattern here? What pattern do you see? F7 is called once, F6 is called once, F5 is called twice, F4 is called 3 times, F3 is called 5 times. What is the pattern?
Fibonacci.
This is Fibonacci sequence again, right?
Yeah.
The number of function calls of these subproblems is a Fibonacci number. I mean, that's fantastic, right? Okay. What is the time complexity? The time complexity, okay, so before, going into that, but you observe this beautiful concept, right? The Fibonacci number is increasing, right? And there is a beautiful identity like this. Fibonacci number and time complexity to compute Fibonacci number. So this is theta of phi power n, right? This is exponential. I mean, approximately 1.6 power n, right? This is less than 2 power n, but greater than 1 power n. So this is a huge number. This is an exponential function, right? any function a power n, when a is greater than 1, it is an exponential function. And exponential functions are damn slow functions, very, very slow functions, right? Even for small values of n, they take a long time, a very long time. Okay, this is about the time complexity. Now let's look at Fn itself. What will be the value of Fn? The value of Fn will be again, right, something close to phi power n, right? Let me write it as theta. Maybe there is some constant factor. You need to verify that. The value of Fn is also in the same order, phi power n. The time complexity is also in the same order, phi power n. And now you know that the number of function calls, right? As we saw, Fn is called how many times? Suppose you are computing Fn. In this, in the recursion tree of Fn, Fn is called once. Fn minus 1 is called once. Fn minus 2 is called twice, right? Fn minus 3 is called 3 times. Fn minus 4 is called 5 times, and so on. So this is really f of, what is this? F of 1, is it? And this
of 0. F of 0.
Is this f of is f of 0?
I think so.
How did we define it? Let's see.
Go back to, yeah.
Right, see, f of 1 is 1.
It's f of 1. Oh,
f of 2 is 1, right?
Okay. Okay.
Okay.
Then f1, f2. Okay.
Right, so this is f2, this is f3, this is f4, this is f4, 5. And do you see the pattern? In the recursion tree of this, fi is called how many times? F
n minus I plus 1.
n plus 1 minus I times.
Then here, I think f0 does not have to exist, right?
F0?
Yeah, because f0 is 0. So probably the lowest leaf should be f1 and f2. But anyway, that's not important.
It's still being called as a base case, so it has to be included, even if the value returns 0.
Then here is, if you go that, you can just say the base case is 1 and 2. You don't have to go to 0.
Oh, I see. Okay, let's see. So if I is equal to n plus 1, what happens? If I is equal to n plus 1, this is 0, right? Is there some problem here? Let's think about it.
Well, you have to include the 0 case because the sum is of the previous 2 terms. So you have to start at f2 in order to get f1 plus f0.
That's true. But if you define the base case as 1 and 2, then you don't go to 2. When you go to 2, it's 1. So the starting case should be 3. 3 is 1 plus 2, right? That's my point. Yeah, but that's not important.
It really all matters on code implementation, doesn't make a difference.
Anyway, so try this out, right? I mean,
anyway, yeah.
F0 is called how many times? Is it n plus 1 times, right?
Yes.
So check this, right? You can verify this, right? For I mean, either small examples.
Yeah, here is 8.
3 and verify that, right?
Yeah.
But take this offline. But this is doable, right? Once we have seen the pattern, try to find the number of times f0 will be called or the base case will be called, right? Either f0 or f1 and so on. That will tell you the complexity of this automatically. And why we are getting this complexity? Because the number of leaves itself is of this order, right? So isn't this beautiful? I mean, it looks like a damn simple recursive algorithm, but there are a lot to analyze here, right? Okay, so try some examples and do some analysis like this, right? Number of calls, and how do you find the connection between the exact value of Fibonacci number and the time complexity of Fibonacci number? And what is the relationship between this and the number of leaves in the recursion tree? You can say F0 or F1, number of F0s or F1s in the recursion tree, right? There is some very neat relationship. All these are related in some ways, right? So try to analyze all these things. Okay, now let's get back. See, whenever you have a recursive algorithm, it means you can create a tree. The execution of that function calls, right? So that is called the recursion tree. And it's very important to write this tree because that gives us a lot of ideas, whether it is an exponential function or the number of calls might be polynomial or something like that, right? It gives us a lot of ideas, the patterns. The branch factor is 2. In some other complicated recursive algorithms, the branch factor might be different for every node, right? Or for every level, and so on. So hence, it's very important to analyze this recursion tree. Okay. Now, we'll see a top-down approach. Of course, the aim is we want to get faster algorithms, right? Phi power n is so slow, damn slow, 1.6 approximately, right? 1.6 power n is an exponential function even for tiny values of n. What happens if n is equal to 100, right? So try doing this. So it goes to a huge number. So we want to come up with faster algorithms to solve this problem. See, here is one, top-down dynamic programming, right? We'll just introduce DP here, dynamic programming. So whenever, what is dynamic programming? Whenever you have overlapping subproblems. What do you mean by overlapping subproblems? Subproblems that are computed again and again and again. See, F5, F5. And we saw that F4, F4, F4. Repeated computations, unnecessary computations, right? Duplicate computations. Why can't we evaluate these once and store it in memory? Suppose we had stored F3 in memory, right? Suppose we store it in memory once. After computation of this once, we can reuse it 4 times, right? Whenever we get F3, we can just call the value in that memory location, right? Reuse, because it's F3, reuse, F3, reuse. 4 times we could reuse the same stored value. F4 or say F2, we could store and reuse it. How many times? Maybe 7 times, right? Because the next Fibonacci number is 8. 8 minus 1, 7, right? So we can store and reuse exponential number of times. That means we can cut off this exponential time complexity and get to polynomial time complexity just by storing. There is no ingenious idea or anything, right? It's really a dumb idea. I mean, if you think about it, it's not groundbreaking or mind-blowing in any way. You're just cutting down recomputations, storing it, right? Just this storing, or you call it caching. See, another example is this, right? On your browser, whenever you visit a web page, suppose you visit a YouTube video or a web page often, what happens? So that downloaded web page or video will be in your cache. And whenever you go to that web page, right, or open that YouTube video link, the cached video will be played there, right? You will not be downloading that video again and again whenever you visit that web page or watch that video. This is called caching, reusing. You don't need to download every time, right? Download once and use it multiple times, unless you remove all history or delete the cookies and all that, right? A similar idea is used in dynamic programming. Whenever there are recomputations, you want to cut off those recomputations. That's why whenever you do the first computation of a function, you store you store the result for those particular parameters. Here the parameter is n, right? So whenever you compute f7, store the value of f7 in a memory location. And whenever you want to compute f7, reuse that stored result. Simple. That's dynamic programming done. Okay. And there are different ways to implement this dynamic programming. One is top down, another is bottom up, right? Let's see top down. So the idea, let's look at the code and then we will see the pseudo. Pseudocode is incomplete here. Let's see the code. So in the code, what do? The first thing we do is initialization. This is top-down DP, okay? Initialization. So you have 0 and you have 1 and all the remaining are set to -1, -1, -1, -1, so on, right? Okay, that means these are unvisited. These subproblems are unvisited. Whenever these subproblems are unvisited, you initialize those with -1, simple. Okay, next, return g of n. What does g of n do? If empty cell computed, that means if you are calling that subproblem for the first time, right? Why is it -1? I mean, now suppose you call g of n here, right? The index is n. If you're calling this for the first time, compute it. That means if the cell is -1, compute it, right? How do you compute it? Recursively call the other two subproblems, g of n -1, g of n -2. If it is already computed, suppose you had a value like 700, something like this, right? Then why do you want to compute it? You just return that value. So simple things, right? It's if else, if not computed, right? If or else if already computed, then return stored value. Simple, right? Simple, very simple logic. If not computed, never computed, not even once. That means if the cell is empty or if the initial value is -1, then compute it. Once you compute it, the value will be changed to some non minimum it will be 0, right? Okay. So once you compute it, you are storing it in a memory location. See? You're storing it in a memory location for that parameter, f of n. You're storing it. When you're computing for the first time, you're storing it in a memory location. If it is already computed, then return that stored value, f of n. Make sense? See, whenever you say f of n, this square brackets means that it is a stored value. If you denote it by this, it means it is a function computed from scratch, right? So this is a stored value, this is a function. So square brackets for stored value, normal braces for function. Make sense?
So Professor.
Yes.
So the trade-off here is that we need an array of n elements.
Correct.
Okay.
Correct. So how were you able to reduce time here? You used extra space, and that extra space is n space, theta n space. I mean exact n space, right? But in the previous, okay, let's think about it. So here, what would be the space complexity? Oh, is it n here also?
Well, you would need to add on to the stack n times.
Right, so it is n here also. Right?
Yeah, it is.
The stack space is n here too.
Mhm.
So it's not really more than whatever this was taking.
Okay, so we're not even really making that compromise.
No. Right?
Actually, you save because the recursive core, you probably have a lot of space.
Right. So it
Yeah.
definitely has more space, right?
Yeah.
It definitely has more space. I mean, for function parameters and maybe something else, and local variables and all that, and it's definitely more. And this is not contiguous locations, so the cache locality will be bad, and so on. There are other disadvantages also. So we are not doing worse in space, actually. It's the same extra space here. Make sense? But we cut down on runtime, and this is a significant improvement. Cutting down or going from a exponential time to polynomial time is a big leap. See, the leap is something like this: exponential time to polynomial time. It's a very big leap. Similarly, from a polynomial time, that is, let's say n squared and so on. So if your functions were taking that to log, I mean, even log is considered as polynomial time, but here I'm specifically considering functions like this: n power 1.5 n squared, so on, compared to this log n, log squared n. This is much better, right? This is a giant leap. This is a giant leap, right? So whenever you reduce this complexity in such big factors, right, it's like a great achievement. Hence, this DP doesn't solve only one problem like this. It solves a big class, an infinite class of problems. Wherever recomputations are there, we can cut off those recomputations and pull in the problem from exponential time to a word of polynomial time, right? So one of the magical wands you use is DP. Make sense? Simple idea, right? Do not recompute. So if there are a lot of recomputations in the computational program, store it, reuse, store and reuse. So, I mean, it is something like this, right? Let's think about it. Suppose there are 1 million schools, right? 1 million schools. Suppose you want to teach algorithms course to all these, and you hire 1 million teachers. 1 million teachers. Now think about recomputations here. What is recomputations? It's the same chapter, same concepts on recursion, right? Same ideas, same problems, same algorithms that everyone is teaching to all these 1 million schools. But instead, if you had put enough effort in making some of the best videos, right? Might be video lectures, animated videos, or whatever. If you had a very huge database, right? Even if you use 1,000 people to do this, everyone can reuse this, right? All million schools, not just now, for maybe next 50 years, say, right? So this is reusing. It saves time, cost, space, a lot of these things. Of course, exams and all should be specific, right? You cannot, it's too difficult to, I mean, there should be someone monitoring, proctoring and all. See, this is one simple concept of reusing, right? Okay, next. Let's look at the tree, recursion tree here. What kind of tree do we get? Let's see. So F7, we don't know the value of F7. We are computing it for the first time. Hence, F7 calls F6 and F5. Okay, first the control goes to F6. We don't know the value of F6. We are computing F6 for the first time. So the control goes to, so we need to compute F6 as F5 and F4. So the control goes to F5. We don't know F5. We are computing it for the first time, right? So we want to compute F4 and F3. So the control goes to F4. Similarly, F4 to F3, F3 to F2. We don't know F2. We are computing F2 for the first time. So F2 is equal to F1 plus F0. We know F1, we know F0 because those are the base cases. We have initialized those base cases. F2 is computed for the first time. And immediately we store F2 here. Okay. Next, we came from, right? We are in F2. We really came from F3. F3 required F2 and F1. F1 is a base case, so we can compute F3 also. Make sense? Now, F3 is computed. Let's move to F4. We came from F4. F4 required the computation of F3 and F2. F3 is done and it is also stored. Now the control moves to F2. What happens? For the first time, you see that a subproblem is already solved. How do you know this? You check the memory location. The memory location is not initialized to -1, right? Or some special character. Hence, you think that the subproblem is already solved. Oh, this one, right? It's already solved. So you take that value and use it here. Use the stored value. Make sense? For the first time, F2 was computed. When F2 was called for the second time, F2 is not computed. We just use the stored value. Okay, now F4 is computed and we store F4 result where? Probably here. Okay, now the control moves back to F5. F5 required F4 and F3. F4 is complete. Now let's look at F3. We first look at the value at F3 here. It is not -1. That means previously it has already been computed. So we can reuse that stored value. Use that stored value and get F3. Right? So later onwards, if you analyze this in the recursion tree, all these function calls, right? You just reuse the stored value. Make sense? So what do you compute really? You compute only these nodes. Look at this, only these nodes. The remaining tree we had here, right? All this tree is pruned because we'll be reusing the stored values and we'll be cutting down this entire computation. Cut down this entire computation. cut down the next computation, so on. Make sense? So does this make sense? So we are really computing the path from root to leaf on the leftmost side. That's it. So it's just one path from root to leaf that has, you know that the depth is n, the memory space is n, the computation is n, and everything else is pruned, right? The recomputations are cut off. Make sense? That's it. That's your recursion tree. This is top-down DP. So the complexity, what is the complexity? N. Space, N. And the recursion tree is shown here. The blue arrow here represents the first computation. The brown arrow here, or box, represents the reuse of already computed result. Make sense? Next. So here is one very inefficient bottom-up DP. So what I will do is I will skip this. You can learn this program on your own. Okay, this is not that important, but it's another way to solve the problem. I mean, you can learn at your own pace. Let's look at bottom-up DP. So how does bottom-up DP work? Now let's analyze top-down DP. So what did we do here? So we started from F7, right? Top down. F7 called F6, F6 called F5, F5 called F4, so on until you hit the base case, and then the value started filling in like this. Make sense? So why do we call it top down? Because the control went from F7 to F6, F6 to F5, F5 to F4, so on. Of course, the filling was really from bottom to top, but the control, right? The function calls, the sequence of function calls was F7 to F6, not F6 to F7, right? It was not F6 to F7, F7 to F6, F6 to F5, so on. Hence, this is called top-down approach, top-down. Now, the question is, maybe we can optimize. How can we optimize? Why do we need to come from top to bottom and again rise from bottom to top? It doesn't make sense, right? We can cut off all these redundant computations of function calls from F7 to F0. We can just focus on the other line from bottom to top. That's what we will do here. Right? Anyway, the computation is from bottom to top, right? And we don't need this function calls also, right? So you can say this is kind of a optimization, right? Of top-down. Let's see how this works. So F0 is 0, F1 is 1. Using these two, you compute what was this? F0, F1, F2. Using these two, you compute F3. Using these two, you compute F4. So on. That's it. Right? The computation goes from bottom to top. You really want Fn, but you will not call a function and come down. You just start from the base cases at the rock bottom. You start from the base cases. Here are the base cases. The base cases are the leaves. The leaves are at the bottom. So you start from the bottom and keep computing the subproblems that are just above the level of leaves. Next, one level above the leaves. So on until you reach F. There is no control here, right? I mean, it's not a recursive function. It's a non-recursive function. You have started from the base case, start from base case, which is the bottom. We consider this as the bottom, and rise up, computing each and every subproblem in the intermediate level until you finally compute the desired subproblem. The desired subproblem is at the top level, right? Fn or LCS or, m comma n, whatever. Make sense? This is your bottom up teach. What are the advantages? So here there is definitely advantage, right? Okay, so let's think about this one. Top down. So the time is definitely n. The space is theta n, but it's not n here. It's theta n. Why? So when you have a recursive function that keeps unrolling, you need some constant amount of extra space for every level, right? So the space complexity is at least 2n. So does this make sense? Because you are defining n at every level, right? And you have an array of size n, so it will be at least 2n. Right? The space complexity is at least 2n. I mean, you can write it as theta n, but it's more than 2n, right? Greater than or equal to. Okay, but what about bottom up? It's exactly n. Exactly n, right? N plus may be constant, right? For I and storing n and all. So it's n plus some constant space. Done. Right? That's one thing. Second, you don't have function calls. No function calls. So you save time on calling functions and storing all those functions, control changing of control, context switch, and so on. Right? So this is typically faster than top-down. Now let's look at another idea. Is anything else that is important here? Yeah, seems like that's it, right? And you can use these ideas, top-down dynamic programming and bottom-up dynamic programming, to any recursive algorithm that does recomputations, right? So how do you cut down the recomputations? You try to store the computation in some space parameterized by the input parameters or variables. Okay. Dynamic programming, it's just converting recomputations into store and reused kind of a thing. And there are two types, top-down, bottom-up. We can also apply divide and conquer on top of dynamic programming. For every DP, you can do that, right? Apply divide and conquer on top of dynamic programming. This is typically not taught in courses, right? This is considered as advanced material. But what we will do is we will apply this simple idea to Fibonacci. It's easy to understand, right? But we will not see this idea in DP, right? You can try to do it on other DP problems, but I will just show you a beautiful, a powerful amalgamation of design techniques. That is, you can combine dynamic programming and divide and conquer together, right? Okay, let's see. Fibonacci of n, we will skip f of 0 and 1, base cases, right? We'll skip base cases. So now let's think that you want to compute 8 of these Fibonacci numbers. I mean, even F9 is also fine. Suppose you want to compute F9. And what is the length from F2 to F9? Suppose it is 8, a power of 2, right? What you do is you split, right? you split this computation or problem into two subproblems. The first half, the second half. Recursively compute each of these terms, right? Recursively compute each of these terms and then combine. Right? You get the final result. Okay, but how do you, like, what exactly happens inside? Let's take a look. Okay, this is on a particular example. Look at this. F of n, the base case if n is equal to 0 or 1, return n, base cases. Else, what you will do is, of course, you will initialize 0 and 1 indices to the initial values. And then you call the divide and conquer function on 2 to n. For simplicity, we will assume that 2 to n is a power of 2, right? That subarray is a power of 2, but you need not assume that, right? You need not assume that. It works, irrespective of that. But it's simple to visualize, right? Easy to understand if you think that this is a power of 2. Okay. Now, you have the divide and conquer algorithm, right? What is the subproblem from low to high? Now, you should have a base case, you should have a recursion case. What is the base case? If there is only one element, right? If there is only one element, what do? You apply a DP. The base case is DP. The base case is DP. One element. Then you do f of n is equal to f of n minus 1 plus f of n minus 2, right? That's a DP. Bottom up DP. Right? Okay. Next. Else, here is the recursion case. You split the array into 2 at midpoint, recursively compute the left half, recursively compute the right half, and you're done. That's it. That's your algorithm. So the recursion here is based on divide and conquer. The base case here is based on D, right? So this is a divide and conquer D. What is the complexities? Same as your bottom-up DP algorithm, right? No change. But of course, there are more function calls here. It might be slower in practice and so on. But that's not the point. The point is you can combine divide and conquer DP. Okay, so here you might not see the advantages, but for other problems, for example, LCS, edit distance, also you can use divide and conquer. Suppose you are filling cells in a DP table, a matrix, you can cut that matrix into quadrants or octants and recursively compute it. What's the advantage? Why should we even do that? Because computing cells in a matrix recursively in this format gives you cache efficiency, right? That means the number of message transfers or page faults, right? The number of message transfers between, say, hard disk and RAM, or RAM to L2 cache, L2 cache to L1 cache, L1 cache to registers and all is minimized. If you use a recursive divide and conquer style of computing. Of course, you're using DP. You're using DP. DP is just the relationship between that cell and other cells. But the way you are scheduling the computations is using divide and conquer, right? This gives you cache efficiency for typically 2 and higher dimensional problems. In 1D, you will not see that power, right? For 2D and higher dimensions, you will see that divide and conquer DP is a powerful technique, right? We'll not consider it later, but just to give you stuff. Okay, time complexity, T of n is equal to 2T of n by 2 plus O of 1. Space is 2S of n by 2. Why? Because there are two subproblems. Remember, left half and right half. Left half and right half. We'll see that the complexity is the same. Okay, next. So, do we really need n space? We don't. We can solve the problem in constant space. How? The idea is this. See, f of I depends on only the previous two values, right? F of I minus 1 and f of I minus 2. So once these are computed, you don't need to store any of the previous results. Those are unimportant, useless, right? Hence, whenever you compute this, you can discard f of I minus 2 variable here. Use this to compute the next one, discard the next variable like this, right? So keep doing this. That is the core idea of this algorithm, right? You can call this as space optimized bottom-up DP. In fact, all bottom-up DP algorithms, right? You can improve the space complexity, right? If you see a problem that has n squared time n squared space, you can reduce that space by one dimension, n squared to n to constant, n cubed to n squared, n power 10 to n power 9, right? You can reduce it by one dimension, right? For to my knowledge, almost all DP problems that I have seen, right, you can space optimize by one dimension, right? Space optimized bottom-up DP. Okay, I will not explain the code. You can understand this code. What's the complexity? Runtime is the same, but space complexity is constant, right? Let's think about it. I mean, should we cover this problem, towers of Hanoi? Probably I will skip this, right? You can learn this on your own. There is a recursive algorithm to solve this beautiful puzzle, right? Towers of Hanoi. So you can go over this. There are also YouTube videos and other resources. You can check that, right? It's a beautiful recursive algorithm. Okay. Greatest common divisor. You know this algorithm already. I think is a very important, famous algorithm that was designed thousands of years ago, right? Several thousands of years ago. And so that means the notion of algorithm was already existing thousands of years ago. It was only formalized very recently. Anyway, so this is the logic to find the greatest common divisor of two numbers, A and B, right? A is greater than B, two integers, and B is greater than B. Okay, now this is a recursive algorithm. You see that clearly, this is a recursive algorithm. What kind of recursive algorithm? Do you call this as a divide and conquer algorithm? This is definitely not a divide and conquer algorithm. Is this a decrease and conquer algorithm? Yeah, maybe this is a decrease and conquer algorithm, right? But the way it is reducing the subproblem, it's unclear, right? It's not very clear. It uses some complicated function than the function we have seen. N minus 2, n by 2, something like this, right? It's a bit more complicated. Okay. What is the complexity of this? We will not analyze it here, but remember that it is of this order, right? The analysis of this is out of scope. Log of min of A comma B, right? Time complexity, SPS complexities, log of min of A comma. Okay. Right. This is the last slide for recursion. See, whenever you come up with recursive algorithms, you should be careful. Why? Now, look at this recursive algorithm. This algorithm or program goes into an infinite loop, infinite recursion. Do not read the comments. Can you see how? Without reading the comments.
There's no base case to stop it.
The base case is there, right? Low is greater than high, return minus one,
Oh, I was just looking at the top, sorry.
right? The base case is given. Oh, I'm focusing on binary search, binary search. Okay, do not read the comments, right? What's the problem here?
You keep swapping back and forth between the middle points, left, right, left, right.
A left, right, no, that cannot happen, right? So we cannot swap between left and right. That means what I'm saying is, see, once you find a midpoint, you decide to avoid the, say, second half, right? You're going into the first half.
Yeah.
The subproblem is reduced by a factor of 2. You will not be touching this again. If you go to the right half of this, you're still reducing the subproblem by a factor of 2. So when
but
you're
here-
always reducing, it has to be of size 1. So that's not the problem.
But here, your 9, 12, you include mid instead of mid plus 1. I think that's probably the problem.
Exactly. So here is the culprit, right? See, this should be mid plus 1, not mid. See, if this is not mid plus 1, what happens?
You get an infinite loop of just scanning the same element over and over again.
Yeah.
Same element again and again, right? There is no decrease in the size of the subproblem. You need to make sure that the subproblem size decreases by at least 1 element. If you cannot prove that, right? I mean, if the subproblem remains the same, then there potentially it can lead to infinite recursion. Here, it is infinite recursion. See, you missed just plus 1 here, right? Just 1 or 2 characters, and your program goes to infinite recursion. So you should be careful, right? So debugging recursive functions is complicated. See, one way is you print out all the levels, right? Print out the level number, and all the variables, right? Where 1, where 2, so on. And you can debug it to some level using this idea. Print the level number. You need to know which level you are at. Okay, what are the variables? Okay, so at this point, suppose you are calling this at the 17th level. So what is the subproblem here? What is the low? What is high? What are the data values? What is the target? And then you can identify, you can recreate that subproblem, right? And try to debug it. Else, I mean, here this is simple binary search, but where a function call in divide and conquer and all, right? Or even backtracking and something like that. It can be too complicated to debug recursive algorithms. Okay, should be careful. Okay, so that's about recursion. We are done with recursion. Now let's move to trees. Now you know recursion, right? Let's move to trees. So tree, so here we will learn the dictionary abstract data type. Dictionary abstract data type. We will look at general trees, binary search trees. We will go deeper in binary search trees. But binary search trees are not the best. Balanced search trees are the best, right? So to some extent, we will look at 2-4 trees. One kind of balanced search tree. There are a lot, 10+ types of balanced search trees, but we will look at one type, 2-4 trees, and the generalization of 2-4 trees we call B trees, and B trees are present in all databases, in all file systems, right? It's one of the most important data structure in the world. Okay. Next, I don't think we will see tries and suffix trees, but I wanted to cover this, but probably we will not cover tries and suffix trees, out of scope of course. Okay, dictionary ADT. See, whenever we start data structures, right, in most of the topics, what do we first start with? An ADT. First, we define an ADT, abstract data type. And then we will look at different implementations of it, the best implementation of it, and so on. Right? Why ADT? ADT exposes a couple of functions, and we are interested in those functions, right? To check which ADT might be applicable to which application, right? Okay, now let's see. Dictionary ADT. What does dictionary do? Let's see. So before that, we want to understand the difference between key, key value, sorted, unsorted, set, multi-set, so on. Okay, let's try to understand all these terms here. So dictionary ADT represents a collection of items. It's a collection, right? Collection, where each item can be key or key value pair. Why do we need this? Okay, we will analyze this later. Why do we need the difference between key and key value pair? Later, right? Key, key value pair. So assume that keys are unique as of now. Now, let's see. So we have a lot of ADTs here. Set, sorted set, multi-set, sorted multi-set, map, sorted map, multi-map, sorted multi-map, right? And so on. Okay. So first, let's differentiate between sets and maps. All these are sets. All these are maps. What is the meaning? Every set, right? So each set is a collection of items where each item is a key. It is a collection of keys. All sets are collection of keys. All maps, right? If we use the term map, it means it is a collection of ordered pair, key comma value pairs, right? Maps contain key comma value pairs. Okay, fine. Now we know the difference between a set and a map. Then sorted and unsorted, right? Let's see the meaning of sorted and unsorted. See, we use the keyword sorted here, sorted here, sorted here, sorted here. When we don't use that keyword, it automatically means unsorted, 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 right? Unsorted, unsorted. Sorted means the items are ordered, are sorted. If we don't use the keyword sorted, it automatically means unsorted. That means they are not ordered. That means if you have an application where sorting is necessary, then set, multi-set, map, multi-maps are bad choices. You want to go for sorted sets or sorted multi-set, sorted map, or sorted multi-map. Got it? Okay, that's the meaning of sorted. Because different applications, sorting might be required, sorting might not be required. Okay, next. Then, what is the difference between a set and a multi-set? You see that two are sets here, two are multi-sets, right? And here also, two are maps here, two are multi-maps. What is the meaning? Whenever you say multi, duplicates are allowed. Duplicates are allowed. It might be multi-set or multi-maps. It means multi, duplicates are allowed. Repetitions are allowed. You can have multiple keys with the same value, right? Same value keys, duplicate keys. Similarly, multi-map here, multiple ordered pairs with duplicate keys. For example, 1, 3, 1,7. This is possible, right? Same key. So these are duplicates. Okay, next. What else? So we learned what are the items in whether it is a set or a map, and we know which is sorted, which is unsorted. Now we know which contains duplicates, which does not contain duplicates. If I use the term set, it means it does not contain duplicates. Map, it does not contain duplicates. Multi-map, it contains duplicates, and so on. Okay, what is the best implementation for all these ADTs? We are covering 8 types of ADTs, right? You will see this often. 8 types. Whenever you use sorted, you use balanced tree. Sorted means you use a balanced tree. We will cover one type of balanced tree later, right? As unsorted collections, you use hash tables. Okay, hash tables we will cover in the next topic. So remember this, whenever you use a sorted set, sorted map, sorted multiset, sorted multimap, they are implemented, right, using balanced trees. Whenever a collection is unsorted, you don't care for sorting. Your application does not require sorting. You just want to insert some items and delete some more items or search some items, but you don't require sorting. Then use hash tables, right? If you're maintaining, say, a student database, employee database, something like that, sorting is required, right? You want to sort all those items based on some ID, right? Then use a balanced tree there. Do not store all the employees in that hash table. That's a bad implementation. Why? Whenever you are asked to give all the employees, right, you want to give that in a sorted order, right? So hash table is a bad implementation there. So use balanced trees if you want your application to sort the entries. Okay. This is very important, right? 8 types of ADTs and their implementations are covered. Next, let's look at map. So map is a collection of key value pairs, key K, V, where keys are unique unless otherwise mentioned, right? Multi-map, we did not say multi-map. So keys are unique. Okay. Why do we care for this key value pairs? Now look at this. Dictionary, right? Dictionary. You have the word, you have the meaning of the word. It's a key value pair. User ID, user record, key value pair. Employee ID, employee record, employees age, salary, work, so on, right? Joining date, so on. That's employee record. All employee record are here. And employee ID is the key. So what are keys? These are unique. All these are unique. The first column is unique, right? Okay, student ID, student record, patient ID, patient record, profile ID, person details, right? It might be your Facebook profile ID. Okay, order ID, it might be Amazon orders, right? Order details, transaction ID, transaction details, URL, unique resource locator, right? Or uniform, something like that. Okay, that's a unique value, unique address. And then you have a web page, full file name, and the file itself, right? The full file name on your system is the key. These are unique. You don't give 2 files the same full file name, right? So all these are the keys. These keys are unique, and all the information related to these keys will be considered as records or meaning other details, right? That's the value. Now, can you tell me, now we have defined key, value pair. Why don't we define key, value 1, value 2, key, value 1, value 2, value 3, all these tuples? why don't we define data structures for all these? Come on, why don't we define data structures for this triple or tuple with 4 of these parameters and so on?
Your value could be a union of a lot of values, right?
Which one?
I mean, your V could be V1 union V2, blah, 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 right?
What is the meaning of union here?
See here, you have a collection of all the values.
Mm-hmm.
Not necessarily each value is listed individually.
Right. So V itself is the record. Suppose you want to store key, comma, value 1, value 2, so on up to value 100. The idea is this itself is the value. You can consider
Yes,
all the details, right? Concatenated details of all this itself as the value V, right? So you don't need to define again, a tuple with 3 values, 4 values, unnecessary, right? This can be arbitrarily large. Okay, if we have k comma v, why can't we have, can't we simulate this also by setting v is equal to null or something? This can be simulated. Why did we define this keys only? Isn't it? If value is equal to null, you can automatically simulate ADT with just keys, right? Isn't it? What do you think? True.
So are you asking if it's valid to have null as the value?
No. So I'm asking, it is valid. I'm saying it is valid, right?
Yes.
Why are we defining this k? We can just use k comma v, and if we want k, we can just set v is equal to null. Why did we define this key? Keys only. The reason is in many applications, right? Many applications require keys only. For example, sorted elements. Suppose we just have a couple of elements, we want to sort them. We don't want to define this value or create a variable value and set it to null. It leads to kind of inefficiency, right? It is true that for generality, this is enough that can simulate every other thing. However, for performance, we also define a collection with just keys and nothing else, right? Just for performance benefits. Okay.
But Professor, if we just have keys with no value, wouldn't that be a set, not a map?
True. So I'm saying we can simulate a set using a map. If you set
Got it. Okay.
right, all values as null, you can simulate all sets from maps. Correct?
Yes, got it. Thank you.
Okay. Now, set ADT. From the homework, you might have seen this, right? Add, remove, contains, add all, retain all, remove all. But the definition here is slightly different. So here we are updating the set S with S union T, S with S intersection T, S with S minus T. So this is the set ADT, right? Okay, we will not go into all these details. So I just want to mention there is a set ADT interface in Java. A normal set is an unordered set, right? Map is unordered map. And this is typically implemented using hash set, hash map. And remember, normal set is unsorted, okay? Sorted set. So in a sorted set, the values are sorted. So you can define what is the first element or the smallest element. What is the last element or the largest element? And you give a value E. What is the smallest value greater than or equal to E, ceiling of E, floor of E, value just below E, value just above E, subset, right? Whether one is a subset of other, right? And so on. So whenever we talk about sorted set, we use tree set and tree map. I mean, tree set is for sorted set, sorted map is tree map. Okay. And now you know that any sorted set or map, right, or sorted collection is based on balanced search tree, right? Multi-set, we will not look at this. You can read about this later. Java does not support multi collections, multi-set, multi-map and all. So you need to use other packages, other libraries, right? The core Java does not consider a collection includes duplicates. It avoids duplicates, right? The keys are unique by default. But if you want to use multi-set, multi-map and all, you need to use extra libraries that are not there in core Java. Okay. Now, so here is a very, 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 very important slide. Okay. Now look at this. What is a dictionary? Dictionary is a collection of items. So in a collection, you want to insert items, you want to delete items, you want to search for items, right? And this dictionary ADT can be implemented in a lot of ways. Look at the number of ways. You can use a sorted set, sorted array, right? In a sorted array, you know that search is log n, binary search. Inserting takes n time. We covered this. Deleting takes n time at most, right? Okay, average case and worst case are given here. I will not cover average case. You can go over this later, right? Worst case. Unsorted list. Inserting is very easy. Add at the end. Deleting of n time. Searching, you need to scan all elements, else you will not find the element. Okay, hashing, we will see in the next topic, right? Hashing complexity is something like this. Binary search tree, we will see a data structure, binary search tree that takes n time for insert, delete, and search. In the worst case, in the average case, it takes log n time, right? Okay, what about all these are the balanced search trees. There are a lot of balanced search trees, play trees, scapegoat, AVL, red, black, AA, AB trees, B trees, so on, right? All your programming languages, right, typically implement a balanced search tree using red, black trees. So whenever you use a tree set uses a balanced search tree, right? Balanced search tree, right? Tree set. So that internally is implemented using a red, black tree, red, black tree. We will not cover red, black trees. We will learn 2-4 trees, right? AB trees or 2-4 trees. Now look at the beauty of all these operations. All these operations are log n time. Insert, delete, and search, everything is log n time. Beautiful, right? Similar. If the worst case is log n, the average case has to be log n, right? Okay. Now look at this. The top of this. At least one of these entries for every data structure, it is n. See, if this is 1, the other 2 are n. If this is log n, the other 2 are n, right? So we are reducing that complexity to log n everywhere. And so that's a big achievement, right? Balanced search trees are some of the finest data structures to implement sorted sets, sorted maps, right? Okay. We will cover binary search tree first, and we will see the disadvantages. Later, we will learn about balanced search tree. I think we are running out of time, right? So probably we will stop here. Okay. We'll continue from the next session.